Okay, good afternoon, everybody. After quite some time, this is first CCAV seminar. The last one was in summer, so we have resumed these seminars, and the last Friday of the month is dedicated to the seminars by NCCAV Center. So, and today's speaker is Mr. Emmanuel Marfo. So the title of his talk is UAV assisted breach inspection, development and testing of an end-to-end operational workflow. Emmanuel is right now a graphics hardware engineer at Intel Corporation. He received his master recently from NCAT in electrical and computer engineering in 2023, and his bachelor degree in electrical and electronics engineering from University of Energy and Natural Resources in Canada in 2017. As a researcher at Access Laboratory, he was researching the integration of UAVs into bridge inspection and automation of defect detection and classification processes into aerial imaging data collection and data analysis. With that, I'm passing it to Emmanuel. Emmanuel, the stage is yours.
Thank you very much, Dr. Karimodini. As mentioned, today's talk is on UAV assisted bridge inspections, and this phase was focused on integrating UAVs into the inspection process after several phases were done on the feasibility and operability evaluations. And Emmanuel Marfo, as mentioned, and this work was supervised by Dr. Karimodini in the Access Lab at CAD. This talk will cover these structured sequence. First, we talk about the challenges that are being faced in the traditional inspections and the opportunities that present themselves for the UAV integration. Talk about the impact of the work we did in the lab. Then go through to the conclusion of what we attain and what we hope to achieve in the next phases. So about the background, a little bit history about bridges in the US. Currently, as per the Ariba data, the US houses almost 620,000 bridges. And these bridges, some are very old, mostly dating back to 70 or 80 years back. And as known, bridges, since they are all structural elements or structural systems, they require consistent and recurrent inspections and rehabilitation. And to narrow down to North Carolina, the state houses almost 19,000 bridges. And in these particular numbers, there is a structural rating which is mostly assigned by the National Bridge Authority and the Federal Highway Administration. And North Carolina has 13% of these bridges as defective, which is way above the national threshold for defective bridges in a particular state. As such, they need to consistently conduct inspection, and bridge appraisals are always on the rise. And bridges, if not maintained properly, can lead to very devastating outcome. Example as shown in the images here, can lead to loss of lives, increase in traffic, loss of property, and other several devastating outcomes that humans wish not to experience. As such, bridge inspections are very important in the US, and the Federal Highway Administration has defined a number of inspection approaches or sequences that need to be done. So with regards to the inspection types, there are generally 7 inspection categories defined by the Federal Highway Administration. And based on the structural makeup, its complexity, the traffic on it, and its location, a particular inspection approach or pattern may be chosen. And in all these inspection activities, the traditional approach has these downsides. To just mention them all, it has proven over time that it's very costly and very time consuming. Looking at the highway estimation for the biannual expenditure on bridge inspection, it's almost $2.7 billion, which is high, looking at the budget set. And aside the cost and time challenge, there's also safety risk that is constantly increasing with regards to the bridge complexity increasing. Now bridges are more complex, and as such, their height, their weight, and their load ratings are also high. As assessing the individual and distinct components exposes the inspectors to several risks and hazards. Example are working at height, using tracks which are not stable on bridges with low load ratings, leading to collapse during inspections. And also, since inspections are not streamlined in a way, it's always it leads to subjectivity and variability in the results. Each person and how he or she sees the results that are being populated. As such, the need to actually define an inspection system which will solve these problems increased. And as such, there's been research on how to take advantage of these upcoming and these emerging technologies like UAVs and other remote sensing technologies to help solve these problems. So in this work, using UAVs, we hope to reduce the time and cost challenge or make them more efficient by integrating UAVs. Also, we hope to enhance the security and safety. That is, reduce the level at which inspectors work at height or work in confined spaces. And also, by using UAVs, we are also hoping to increase accessibility to some distinct aspects of the bridges. And we have to create a system or an ecosystem where we can repeatedly repeat the same results, even if it was done by different people with different inspection skills and knowledge. And also, we need to make it more faster. So we need to have an enhanced and real-time audio system which can, in real time, monitor and analyze and also report the findings to bridge stakeholders and bridge owners. So jumping to the focus, as mentioned, to solve these issues, we need to really hit on some particular points. The first point is the restrictions that are being imposed on UAV integration, UAV usage by the FAA. And the commonest one is the airspace class. There are class distinctions or definitions for which UAVs may or may not fly in the US here. So it's prudent the inspection team and the researchers go over the restrictions and apply for waivers if possible to be able to conduct an experiment. Also, there's a need to analyze the battery life and flight time. UAVs have limited batteries and battery life. So we need to understand the integration process, what it comes with, and what to make available to avoid failure or drawbacks. Also, we need to understand or have a system that will help us in interpreting the data we collect, be removed in real time or even the post-inspection phase, so that it will reduce the happenstance of variability and different analogies or different validations based on different knowledge and skills from different personnel. And since not all bridges may qualify for UAV integration, we need to also develop a system that will help us to evaluate a particular bridge to see if it fits for UAV integration. And we need to have a system that will help us detect ahead of time if the bridge schedule is appropriate. So the ultimate goal of this research is to develop a workflow that will aid in the technology transfer from research to implementation in the field by assisting the inspectors in understanding the deployment phases and processes involving UAV integration into bridge inspection. And the objectives of the work are as shown to the right side. So in the end, as mentioned, we hope to achieve these three main factors or three main goals: enhance the inspection efficiency, cost and time, particularly the safety aspect, reducing the risk, and increasing accessibility, as mentioned, also making our results more reliable and more repeatable. So in our work, in accordance to the current inspection process, bridge inspections are categorized into three main stages. The pre-inspection, which houses the in-office activities and on-site inspections, on-site evaluations, and then the actual field activities that involve the data collection and analysis, if there's a real-time implementation in place, and the post-inspection phase, which involves the data analytics, the detailed data analytics, and also report generation and stakeholder meetings. So to start with the inspection process, in the in-office, we try to go by the traditional approach, not to bring or introduce a huge difference in practice from the get-go. So this sequence or this workflow is in line with the traditional practice that to start with, the stakeholders or the inspection team evaluates the documentation. They get to know the bridge history with regards to maintenance data, maintenance history, what needs to be done, what has been done earlier. And then in the next stage, we try to integrate, where we kickstart the UAV integration. So at this point, we do the bridge candidacy evaluation, which is the bridge fits for UAV inspection. And to do this, we shortlisted some key metrics or points to focus on, particularly the bridge size or its height or its complexity. Because some bridges are short enough to not warrant UAV integration. And how accessible the bridge is, the location of the bridge, the cost effectiveness, looking at the previous inspection report, how much was spent on the bridge, the time was spent. If all these criterion are marked or are assigned higher scores, the final score from the candidacy evaluation table will inform the stakeholders on the approach, either to go by UAV integration or proceed with the traditional approach, which has always been the practice. So in the end, after everything in the integration phase, this particular table will be designed in a UI form or in an integrable form into the current system that is used by the NCDOT, which is called Wiggins, so that in real time they can do this analysis together with the planning in the office to know what to go by during the actual inspection phase. And after being able to evaluate the bridge candidacy, we can now proceed to selecting the platform. Knowing the bridge we are working on and the objectives for the inspection will best advise on the platform to use. So this stage will be dealt with as a result of what is being obtained in the previous phase. And in the previous phase of the inspection of the research, the team was able to develop this particular template that will be used to evaluate several platforms to be able to understand which one to go by for a particular bridge inspection activity. And after being able to select the bridge and having selected the particular platform to use for the inspection, so now be time for us to plan the inspection properly. And in the planning phase, you have to understand the time that we expect the inspection to last or span, the number of resources we need, be the team, the batteries, the standby resources we need to make the inspection happen smoothly. So in our work, we defined a flight path or a flight sequence, which after conducting several experiments, realized it was best to be used. And in that phase, in that experiment, we defined 4 different flight paths. The first is the vertical. The vertical is just top to down or down to top flight over the vertical elements in the bridge, particularly the piers, the columns, the bends, and the pillars, just to name it. After this, we define a longitudinal flight, which in our definition travels or flies along the x-axis for a regular 2D element, if you have to make the bridge a 2D element. So in a typical bridge structure, this flies along the girders or the beams or the rails, the actual railroad. So that is the longitudinal section. And the horizontal is the opposite of the longitudinal. We cut across the road from shoulder to shoulder, or from shoulder to shoulder, to make it more easier, more simpler. And lastly, not all elements on the bridge will qualify for the first defined 3 sections. Examples are elements that are at the top notch, or bolts, or bearings. Those standalone elements cannot be inspected with vertical or the other two flight paths. So now we define a standalone inspection category, which will just focus on those standalone elements. And after being able to define the flight path that is preferred for the inspection conduction, it will be wise to estimate the time that will be used in this flight or the total inspection approach. And in our approach to estimating the time that will be required for an inspection to be conducted successfully, we first, as I said, define static paths for our bridge elements. So as said earlier, the pile or the bend, the columns, the pillars are the vertical elements. The power cap, the girder beams or the grade beams are the horizontal, and longitudinal elements are the girder themselves or the deck road themselves. So after these definitions, we first did an experiment to understand the skill level of a pilot who will be employed to fly the drones or conduct the inspection. And in that experiment, to understand the flight skill levels, we defined 3 flight categories: a basic pilot, a professional, and then intermediate pilot. So these 3 skill levels were defined, and we had a series of flight experiments with these separate pilots to understand the timing or the time sequence they go through in successfully inspecting elements or the whole bridge. After these phases, we're able to calculate the required speed or speed ranges for which a particular pilot skill level can fly the drones and give us an optimum or optimal output for analysis. And as shown in the green box table, we're able to define the ranges for the pilot skill levels. Having defined these ranges, we now use one pilot skill level to estimate the time it will take for us to conduct a bridge inspection. So using this bridge, which has 10 spans and each span has almost 66, it's almost 66 foot long to regards to the length, we're able to design a tool that estimates the inspection time. And as shown here, using this bridge and the dimensions given in the previous slide, having a pilot with the professional skill level and setting the speed to 2.5 mph, it was estimated that the pilot would take nearly 2.5 hours to conduct the full inspection. And this estimation includes a 30% margin of error, which can be attributed to the fact that there might be difference in wind speed at that time, or the weather might cause for there to be several break and resume sequences in the inspection. And having known the inspection time, we can quickly compute the resources we need with regards to batteries. Since each drone battery lasts, let's say, 30 or 25 minutes, we assume that the manufacturer stipulation there is, it's not as an assumption, it's a fact that the manufacturer stipulations there are with regards to room temperature. So in our estimation, we assume that 85% of the battery can be used. The remaining 15 will be lost due to the environment we are in. So having a battery of 25 minutes of flight time as manufacturer specification. We had 20 minutes of operating time that can be used by the drone. And having achieved these values, we're able to compute that a 2.5-hour flight time would approximately require 8 batteries. And this insight will guide the inspection team to understand or to know what to go to their field with. Because most drones come with at least 3 or 4 batteries. So requiring 8 batteries will indirectly communicate to the inspection team that they should plan for an excess storage or power bank or energy capacity where they can recycle the batteries so as to not pause and resume or face any unplanned instances which will result in increasing the total inspection time. And that is not what we are hoping for, we are hoping to achieve. So all these insights will be modeled in the general workflow that will be transferred from the research phase to the implementation phase for the inspection team to apply to their inspection activities. After these estimations and understanding all these things, we can now jump to preparing for the inspection, which is almost similar to what they do in their traditional sequence. Gather all the items, make sure all team members are informed on the date and the scheduling, and everything is gathered before the day of inspection. And since we are transferring the technology from the research labs to the field or to the field to be general, we have to also make it easy for the inspectors to understand how to go by using these drones or frequently servicing and updating them. So we designed a simple flow which applies to almost all drones that we have in our lab. This design was added because of some incidents we faced. There were happenings where the team got to the inspection site and realized the drone actually required an update. And as such, we were not able to fly the drone. You have to drive back hours to the office just to update the drone. Or you have to drive back to a site where there's internet. Most bridges are at remote places where there are no or less or weak internet signals. So you have to drive back to places to get a better signal to update it, which all adds up to the inspection time and literally to inspection cost. So we added this to ensure that the inspection team or the inspectors conduct all these activities to optimize their in-field inspection time. And in the final stage of that, after the in-office activities, we just sign off by having this UI or software developer, which will just let them check off whatever item is needed for the inspection to be done. At the site, there are some basic things to be done. Check the safety plan, have a debrief with the team, and in the next stage, there is a mandatory it's a mandate from the FAA, which says that for any UAV outdoor inspection or outdoor flight, it's supposed to be a visual observer who at any point in time will keep his eyes on the drone and communicate with the pilot as to incoming traffic or any damage ahead. So in that regard, it is wise that the team set aside special people who will act as observers. And in the same way, to optimize the team size, it is best the team also decides that among the teams, people multitask so as not to increase or introduce any extra team member just for the job of observer. So all these are handled in the pre-inspection phase before the actual inspection is started. And in the field inspection, currently in our work, we limited our resources to only RGB-based UAVs. There are several sensor technologies there, thermal and among the rest, but we use only RGB cameras for our inspection or for this phase. And in using RGBs, we define 3 approaches to conducting the inspection. The first can be collect overlapping images, which are basically videos, and then we can run the videos through an optimized or a developed algorithm, which will help us analyze the respective displacements that are recorded in the video, or collect multiple images with a high overlap to avoid missing any damage or any defects. And then we can run an algorithm on it to draw contours or bounding box around the respective defects detected. And the third is to employ 3D reconstruction, where the bridge can be modeled as a digital twin. And then on a digital twin, you can now augment the respective defects on it. And in going by these, any of these, this workflow is applicable after we check all the systems and we get to the 3D modeling part. We just ask or pop up a question for the user or for the pilot. If we are not employing 3D reconstruction, we can now jump straight to in the event that we are employing 3D reconstruction, we have to kickstart the 3D modeling phase of the work, which will have to remodel the bridge. If the model is not already available, we have to build the 3D model by collecting overlapping images to build it first before we now conduct the inspection. But if there is the 3D model already built for the bridge, you can go straight to inspecting and then augmenting or filling in the respective phases with the current stature of the bridge. And during the inspection process, if there is a real-time system established which can communicate in real time the defects, be it with bounding box or contours, the system will be kickstarted. If not, we will collect the necessary images or videos and then save them for post-inspection activities. And if there's in our work to have a real-time system established due to how heavy the deep neural network systems are, we sought to quantize or compress our models so that it can be used on edge devices. And there are several ways to do that. You can prune the model. Pruning it will do away with unused or ineffective weights and neurons that are just located in the huge network. You can also conduct knowledge distillation, which is quite different from knowledge transfer or the transfer learning. And also you can do quantization, where most of the algorithms in the neural network are 16-bit algorithms or 16-bit variables. You can quantize them to 8-bit or 4-bit, which will drastically reduce the network size and complexity, but keep the accuracy and metrics intact. So in our work, this is the structure of our real-time system. While the inspection is started, we load our model and we stream the video or the overlapping images into the system, and we conduct the real-time inspection, and the inspector is there to validate the predictions from the model. But this is a UAV assisted inspection. It's not overtaking the entire inspection approach. So the inspector validates the output from the UAV before it is being saved or is being assumed as valid. And to achieve the real-time effect, we try to use the model pruning approach. By pruning, I mentioned, is just to reduce the number of connections, the number of neurons in the entire system, just to arrive at a compressed model with smaller size but equal performance as the parent model. And in the event that the real-time inspection cannot be started, the data collected cannot be used or cannot be analyzed in the post-inspection phase. Also, after real-time inspection has been done, the data can still be analyzed intensively in the post-inspection phase. And in this phase, we design a simple workflow or a simple sequence to guide it. Depending on the data type that was recorded, we pass it through the appropriate processing models or algorithms. So for 3D reconstruction as known, we pass them through the point cloud processing. Or for video and images, they go through the visual analysis algorithms. And in our work in our data processing, we first use the respective image processing techniques to put our images in the best shape before they are passed to the algorithms, as has been the practice for computer vision and all these image processing techniques. And afterwards, we do our analytics. And as mentioned, this work was mostly focused on images and videos. We didn't consider point cloud that much, so the section for structural analysis is not dealt with in this phase. So in the visual inspection section, we use machine learning algorithms coupled with computer vision techniques and AI to achieve our output. And the first work, we considered an instance where the visible defects on the bridge are just cracks, only cracks. So in that, you have a set with cracks and no cracks. And this is the sequence in which the algorithm was developed for conducting the data analytics. We first pass the images through an image processing technique to filter or put it in the best shape. And the algorithm will now detect and classify the cracks. And then you can now quantify it if possible. So a sample of images that were used in model construction are shown. So in the processing stage, we first use O2 to binarize the images. There are several ways to binarize them, but we use O2 to do the binarization. And after the O2 implementation, the sequences that the O2 goes through are shown in the images here. So the final image after morphological operations is the fourth one to the right. And having this O2 binarized image, the image can now be passed through the algorithm. And in our system, it was a very lightweight neural network. And these are the parameters that we use or we tuned during our training and implementation. And after the crack algorithm development, the testing phase showed that the algorithm was able to detect and classify cracks on concrete surfaces, as can be seen on the confusion matrix with at least lower misclassifications. And afterwards, we did the real-time implementation on a surface where we have two ways. Either we use the contours to select or pinpoint the defects, or we use bounding box to also do the same thing. And after dealing with cracks, it was realized that there are several types of defects on bridges, not only cracks. As such, we had to remodel the system to help us solve the issue of which type of defect is this. And in that way, we retuned or remodeled the model by using 4 defect types. Okay, 3 types with no crack as the fourth class. There are several defects, as said earlier, but the commonest ones that we came across on our bridges are these 3. So we use them to model our machine learning algorithm. And this is a picture of how these respective defects look like. So to start with, in our data set, we had a limited number of images. So we defined an algorithm which did these operations on the respective images to result into a balanced set with 3,000 images each in all the respective classes. After this image augmentation phase, we employed transfer learning, where knowledge acquired from datasets, which are large in number, is borrowed. And then based on that knowledge, we develop or we fine-tune our model to achieve a final model which is optimized enough to handle our task. And in our work, we use ensemble learning also to aggregate the predictions from multiple models or multiple fine-tuned models to result to a single model which can handle almost all cases with regards to types of defects that we are dealing with. So we chose these 5 architectures based on their diversity and their difference in implementation and in construction. After the ensemble approach, earlier in ensemble too, there are several ways, but the 3 common ensemble techniques are bagging, boosting, and stacking. Bagging is mostly used for regression runs, and stacking is mostly used for classification. So in our work, we use the stacking. And the stacking is just the idea is you run separate models on the same data set, and you can either stack their outputs as one, or you can stack the models first as one, and then you pass the final output to a meta classifier, which tries to understand the basis upon which the respective models make their predictions, and then make a final prediction from those inputs. So in our ensemble or in our stacking ensemble model, this was the sequence we went through, and this was the structure of the neural network that we used. And in evaluating our system, we chose these 4 metrics for the evaluation. After training and running the module several times and fine-tuning it, we had these results from the respective base models that we chose for the ensemble model. As can be seen, VGG19 occasionally emerged as the best model for handling the dataset we had. Same was the dense net model, followed by the exception model. Afterwards, we now did the ensemble aggregation, and then the final ensemble model proved to be best among the models that we had in the final implementation. So compared to the 5 base models, the ensemble was able to aggregate the respective predictions for and achieve a higher prediction or a higher accuracy or higher metrics than the individual base models. Afterwards, we just did a regular run on a sample set of images with that contains it contained 200 images of 4 classes of defects, and it was able to classify the respective defects into their appropriate classes, as can be seen in the image here. So to end our work, we were able to identify the challenges that are associated in bridge inspections. We were able to optimize or take opportunity of the defect challenges and capitalize on that by integrating UAVs. We were able to develop the workflow that will guide in the transfer of technology from the research labs to the field. We were able to provide systems that can estimate or predict the inspection sequence and timing, for us to have a better view of what to expect and what not to expect. We're able to also provide algorithms or systems that can help us achieve repeatability and reduce the variability in explaining the inspection results. And we're also able to provide a system that can, in real time, enhance the inspection approach by assisting the inspectors with what to expect, what not to expect. And in this work, everything that was achieved is limited to the data set we had from the onset. So having these models there, it can be repeated or it can be varied or it can be optimized by using different data sets or making them more improved or more advanced. Also, this work did not really talk about the cost benefit, because that session will be covered in the next phases if it will be conducted, to understand the cost and timing benefits by striking a comparison with UAV integration results against traditional inspection results. And also, we can make this workflow and these softwares more user-friendly by implementing them in various and commonly used softwares or software languages. And lastly, you can improve the model accuracy and its entire metrics, as I said earlier, by incorporating more richer images and more diverse images, and even increasing the number of classes, since there are several defects in real applications. So you can make the work more applicable and practicable by making the number of classes more diverse and increased. So this is what we worked on for the 2 years in the lab on the web integration. If there's any question, I'm available to take them. Thank you.
Great, thank you so much. So, any question to Emmanuel? By the way, congratulations, Emmanuel. Just today noon, you got the acceptance letter for the TRB conference. That's great.
Yeah, I do have one question. Can you hear me?
Yes.
Okay. Yeah. Thank you, Emmanuel. Yeah, good presentation. Yeah, you have done a lot of work. One quick question that's very simple. Is there any, so you're using also thresholding at the pre-processing steps. Is there any advantage of using that before the training, or we can simply take the data and then we can directly feed that to the neural network? That will also work, right?
Yes, there is not much of an advantage in binarizing the images first, but some applications would do great if you binarize first, but not always. It's not always the case. You can, in our work, we tested a system which took only the images in the color sequence, but most of these algorithms do best when the images are grayscaled. And in grayscaling it's just good you binarize it properly. That's why we use the O2. But there is also a system that we have which takes in the RGB images straight and provides almost the same or similar outputs.
So yeah, basically binarizing will probably need few data sets. So data pruning will be basically gives good result. Yeah, thank you. Yeah, one other thing. So can we, so you're using data, so can this data be accessed, or let's say for some other neural network training, how do you, if you want to work on this field, how can we access those data?
Okay,
is that publicly available?
We are working to making available on the Access Lab GitHub page. I think it's still in progress, so we'll make it available on the GitHub page where the write-up and everything together with this work will be available for public consumption. But as of now, it's not available, but I think it's a work in progress.
Okay. Yeah. So if we want to use that later, we can contact you and use that data whenever it's publicly available, right?
Yes, you can contact the lab. The lab will grant access to everything you need since it's lab property. But you can always reach out to the lab. You can assist you in whatever you want to do with it.
And we can work, Dr. Sanil, we can work and even early results we can share with you. And thank you, Emmanuel, for the great talk today. And have a wonderful weekend, everybody.